Let's consider one more spherical symmetric distribution of charge. Here we have a thin shell plus q, so this is a thin shell. And we'll just denote the radius of the shell by a, and we're neglecting the thickness of the shell. And we're going to surround that by another thin shell of radius b, where we have a charge minus q. So we have two thin shells. And I'd like to find the electric field everywhere in space. And we have three regions of space. Now, I want to do two of those regions very quickly. So for the region 3, I'm going to pick a Gaussian surface of radius r. And in region 3, there's no charge enclosed. So the electric field inside is 0 for 0 less than r less than a. Why? Because there's no charge enclosed in our Gaussian surface. If I do the same thing in region 1, so for r bigger than b, our flux equals q enclosed over epsilon naught. Well, the flux is the usual. Let's just conjecture that there's an electric field. We don't know yet. We'll just conjecture, but it has to be radially outward. So this side would be E1 times 4 pi r squared. But the charge enclosed is plus q, this one, and minus q, the outer one. And so that's 0. And so once again, we conclude that the electric field outside the shells is 0. And this is r bigger than b. And now, if you wanted, you could think about this as a superposition problem, where you just calculated the field of a negative shell and added it to the field of a positive shell outwards. Both shells act like point charges at the origin when you're outside them. And so the sum of those two fields will be 0 because one is negative, the other is positive. We just did it in one fell swoop with Gauss's law. So now region 2 is the one that's of interest. And I pick another Gaussian surface. So this time I'm picking all of my Gaussian surfaces on the same diagram. It's sometimes nicer to see them separately. And now we're in the region r less than rb. And we apply Gauss's law to this region. And what we see is that the charge enclosed, all of the inner shell is enclosed in the Gaussian surface. And so we get E2 times the area of the Gaussian sphere is equal to the total charge plus q divided by epsilon naught. And so our conclusion is q over 4 pi epsilon naught 1 over r squared r hat for the field between. And once again, this result is no surprise, because in this region, the inner shell acts like a point charge at the origin, and that's the electric field of a point charge at the origin. And now you might ask, what about the outer shell? But we've already proved that the electric field inside a shell is 0. So the outer shell makes no contribution to this inner region. And we just have the field of the inner shell treated as a point charge at the origin with its characteristic 1 over r squared radially outward direction.